So my name is Rafael Benevides. Thank you so much for being here. I'm a director of developer experience at Red Hat. But essentially, I'm a Java developer. Okay, that's my background. So I bet that all of you are Java developers or are involved with Java somehow, right? Because that's why you are here. That's why you are so interested in this talk. But before before going deep on the Java, on Docker problems, since you are all Java developers here, I cannot start without promoting or talking about the microprofile I/O specification. How many of you heard about the microprofile specification, right? Okay. The good thing about using microprofile specification is that you can use Quarkus. Have you heard about Quarkus? So for those who haven't heard about Quarkus, let me show you how cool it is. Because, for example, if you go to the page quarkus.io, you will find some examples here. Let me go to get started, creating your first application. Nothing special here, it's just a Maven command. Let me just run this Maven command here. So it has already created the project. Again, nothing special. Then I'll go to getting started and do a regular Maven clean package. Until now, nothing new, but it created an application with using microprofile. And the good thing is this. First, if I go to the target page and do a ls/lh, let me get here, getting started. Look the size of this jar, 42K. Okay. Of course, most of the embedded things are inside a lib folder. That's not huge, it's like 8 megs, less than 8 megs. Okay, but let's run this jar. Java-jar, getting started, runner. And it's running in less than 1 second. So it's a Java application that started in less than 1 second. And believe me, this is not a lazy loading initialization. I can even open here the localhost page. You can see that the application is already running. There is even endpoint here, API, hello. It's not hello. Let me see what's the address that I used. Yeah, it's /hello. Yeah, /hello. So let me just, and again, it's running. It was fast to start. It is small on the disk, but also, if I look here at memory and look for the Java process, it consumes less than 100 megs of RAM. So this is really important because nowadays, if we have a cluster and 10 servers, 10 nodes, we can place probably 100 applications there. But if we reduce the memory consumption of application, we can increase the density and have more applications running. So that's the good point. And because David just told us about the serverless. So imagine an application that can start in less than 1 second. That's good for serverless purpose because it will start serving requests, and it will be good to be discarded after that. But that's just something that I wanted to share with you. Okay, what is this? Okay. Let's return about the possible issues that can happen with Docker inside Java. Java inside Docker, in fact. This is based on this blog post here, this talk that I wrote in 2017. And believe me, certain problems still exist. I published that like almost 2 years ago. And it became very popular because people were excited about containers. people are still interested in Java. That's good. We say that Java is not dead, but they started facing some problems and they didn't know why. So the first question for us who are Java developers, we know that Java is meant to be portable among different machines. So why we take a Java application and place it inside a container? Is it because it's portable also? Because we can place everything inside, not only the application itself? Yeah, if you think for a moment, when we are taking our application before containers and sending it to the production, we need a server, an operational system, the JVM running, an application server configured. Like, for example, I want WebLogic, I want EAP, Tomcat. Then we change the configurations of that server, and then we place our WAR file. And usually, we send an email to the production guy saying, OK, please create that environment to me. But when we are using containers, we just rely on the Docker file to specify everything that we need to run a Java application. So that makes things even easier. We are not just giving the jar file, throwing it over the wall to the production guy. We are sending a container, an image that has everything that is needed to run a container. But Java was meant to run freely inside the container with a lot of space. Java came from an era where it was meant to run alone on a server, so he could use his JVM ergonomics and stretch and feel comfortable inside it. The problem is when we decide to create a restricted container. And we'll see that by applying some limits. Because what happens when we decide to run a container? Docker, for example, uses two Linux features. It uses cgroups and namespaces to create a restricted process. And then, of course, to control what is running inside that container, inside cgroup, we have some information, for example, like the memory information. It's written in a file. But containers started to become very popular in year 2000. And just in 2013, that .cloud became Docker. So we started hearing about containers very recently, just from 4 years ago maybe. But Java came before that. Java started in 1996. Okay, so what's the problem? Let's get, for example, let's start in some demo here. I will run, as I said, the problem starts when I decide to run containers with restricted memory or restricted CPUs. So what I will do here is start a container, a CentOS container, with the command docker run. I will assign a terminal. --rm means that I will discard this container after the execution. And here, I'm limiting the memory to 100 megs. Okay? And the swap is also 100 megs. And I will run the command free -8 to show the free memory in a human-readable form. By the way, let me just show the configuration of my Docker instance here. I'm using Docker with 2 CPUs and 2 gigs of RAM. What the command free showed to me? That I have 2 gigs of memory available and 1 gig of swap. And you might start to wonder, okay, but you specified a memory limit of 100 megs and 100 megs of swap. So is that a bug? Maybe it could be a bug on this distribution. So to prove that's not a bug, I will run another distribution here. Instead of CentOS, I will run Ubuntu. And the result is essentially the same. 2 gigs of RAM, 1 gig of swap. And you start to wonder, well, if it's not a bug on free, so this command -m or dash memory swap does not work. We can think about that. So let's start to run a Java application with a more restricted memory limit. So I will run here a container that I will call my wildfly with just 25 megs of limit. So I'm running here JBoss wildfly. So imagine an application, a Java application with just 25 megs of RAM. So we can run that. I will just show here the Docker stats. And we can see the my wildfly container. And also, let me run it again. Docker rm my wildfly. Let me run 25 megs of limit. And we can see that the limit here, 25 megs. We can see the percentage use of CPU. And it seems that it's getting closer to 25 megs. We have a lot of CPU activity here. This is the CPU. So we see that it's consuming almost 200% of CPU. That means that the 2 CPUs from Docker is being used a lot. And then what we see here on the console is JBoss process received a kill signal. So that's the main point of this talk. When we say restrict the memory to a certain limit, we are not saying that this operational system will have 25 megs of RAM or 25 megs of swap. We are saying if the process tries to consume more than 25 megs, then the kernel, the Linux kernel, will send a kill sign to the process. That's why the application died, even if it sees the 2 gigs of RAM or 2 CPUs. But let's also do a post-mortem analysis on this container here. Let me do a Docker inspect. Docker inspect my wildfly container. When I do that, I can see what happened to this container here. It died, of course. It's not running anymore. You can not see it here in the Docker stats. But we can see the state of the container. So the container status is exited. It's not running. Running, false. That's OK. And it's not paused. It's not restarting. What happened to this container is that it was OOM killed, out of memory killed. It was killed because it tried to allocate more memory than it was allowed. So that's the problem. When you try to restrict Docker, things can go wrong, right? And let's see what else, what are the things that we can do. We can, to demo some things here, I prepared a Java application. It's a Spring Boot application that has 2 special endpoints. One special endpoint here will get it will use runtime, get the max memory, and start to create strings. As we know, Java strings in Java, they are unmutable, and until the used memory, so you can see here it loads the total memory, gets less than 80% of usage. Okay, so let me run this application here and see how it will behave. So let's run it with the command docker run -it -rm, because I want to discard this container. This container is called my container 150 because I'm limiting the memory to 150 megs. So let's run this. You can see that the application is starting. We can see here on the Docker stats that's limited to 150 megs. And the application has started. So 150 megs seems to be enough. Almost 90% of the limit was occupied. So let's access the application in my special endpoint called API memory. When I access API memory, you can see here it's starting to allocate memory and killed. Well, it was not supposed to get killed. Let me see here, 2 gigs of RAM. Let me see here, starting to allocate memory. Let me reduce a little bit more of memory here. Instead of 150, let me give let me see here. In fact, what I will do is reduce a little bit of memory. Okay, note here that with 1 gig, with 2 gigs, the application is being killed. What I will do now is reduce the memory. So what do you think that will happen now? Because of my face, you can see that it will run. But the question is, why? Why I'm reducing the memory and the application will run this time? So let's wait to the Docker daemon to start. Of course, it takes a while. And the application is running, okay. And let's do Docker stats here again. So the application has started. Let's access our endpoint. So it's starting to allocate memory. Again, I ran this application with 150 megs of limit. No, and killed again. Oh my gosh. Why you have 2 gigs, 1 gig, and you are dying? So let me reduce a little bit here. Let me reduce to 140. Okay, we can see oh, okay. So what's the point here? I wanted to make this application to be able to execute with 1 gig of with 1 gig of RAM, and let me just reduce even more, 1 meg of limit. Okay, let me give more memory. It's always hard to do this kind of demo because it needs to be to perfectly match the values, and that is one of the reasons that we want to learn how the JVM. Yeah, that's it. How the JVM behaves when it's related to the JVM ergonomics. So what happened here? I gave 180 megs of limit in this container. And the application allocated 241. So here we have a problem, a specific problem. And we can have 2 questions here. One, we saw previously when we tried to access more than 150 megs, the the Linux kernel sends a kill sign to that process. And here, it allocated 200 megs, which is more than 180, right? But it calculated the maximum amount of 241. So the first question is, why it allowed to run 241 and it didn't kill the process? It happened because when we specified here 180 megs, it created 180 megs of limit in the RAM and 180 megs in the swap. So everything that is over 180 megs, as it happened here, it will start to send the extra amount to the swap. So in a container with 100 megs, 180 megs, we can run 360 megs of process. And I just requested 200 megs, so it seems to be enough. But here another question. Why the JVM said that the maximum amount is 241? That happens because if we take a look at the Oracle documentation for the Oracle JVM, we will see that based on the characteristics of the machine, it will make it a client class or a server class machine. A server class machine is any machine that has 2 or more processors and 2 or more gigs of memory, of physical memory. In this case, I have 2 or more physical memory, remember? 2 or more physical CPUs. And then, what it applied as a default value, it asked that the maximum heap size is 1/4 of the physical memory. So in this case, my Docker is configured to have 1 gig of RAM. 1/4 of 1 gig of RAM is approximately 241. That's why my JVM configured itself to allow 241 as a maximum, and it was not killed because the extra memory was sent to the swap. Okay, it's a little bit tricky, but we can think, always think that some problems can happen when we decide to send things to production. Because usually it can work on our machine, like an 8 gigs developer workstation with 4 cores. But what happens if we increase, if we take the application that's working now and send that to production with more memory and more CPUs? So what I will do now to show the point is increase the memory of everything. Now I want to have 8 gigs of memory. And it's not only that. I will also run a container with 600 megs of limit. So I increased from 1 gig to 8 gigs. My container was limited to 180, and I'm increasing to 600. And based on what I said, what do you think, while the Docker daemon is starting, what do you think that will happen to that container? Just do the math. Will be enough? Who? Yep, it will run. Nope. Why will not run? That's great. So remember, the JVM ergonomics will think that the maximum is 2 gigs. Okay? But the limit here of the memory is 600. 600 in RAM, 600 in swap. But the application will try to allocate, let's see here, 2 gigs. 2 gigs is more than 1.6, and the application will die. Now it's taking more time. Let me run Docker stats here. Yeah, and the container killed. So again, me just reduce here. It's trying to locate 600. The application is running. Let's request more memory. We can see a high usage of CPU because it's trying to do garbage collector and send everything to swap. You can see the amount of gigs here because it's doing disk I/O, and then the application killed. So it's good for you to know about this JVM ergonomics. Otherwise, you can face that problem. You can take an application that's working on your machine, place it on production, you increase the memory of the container itself, and the application got killed. So that's the point. Now we'll learn how to make it work. It's not just about showing the problem. I'm here to help you to identify possible solutions. So, my application here has several Docker files that I'm using for this demo. This one is just simple. It just do a java-r, and I let the JVM ergonomics to do the calculus of how much memory I need to run my application. What I did in this other Docker file here is that I introduced environment variable. So in this case, I'm not relying on JVM ergonomics. I'm saying to Java, I want to specify the maximum amount of memory. So here, I still have 8 gigs of RAM, but I can run a container. Oops, not here, but here. Specifying an environment variable with -e Java option and saying I'm locking the maximum amount of memory to 300. Okay? Now, the JVM ergonomics will trust in me, not on itself. Okay? So let's run that same endpoint again, and the maximum amount of memory is 300. So 300 is enough. I can run even, since I have 8 gigs of RAM, I can run multiple containers. I can run at least 10 containers here. No, not 10, but 20 containers with the limit of 300 megs. The application is not run it didn't crash, and it works amazingly well. But it still have a problem. Every time that I'm running an application, I need to know how much memory it's enough for this application. In this case, I suppose that 300 memory is okay. But there is a project called Fabricate. Let me just open the page of Fabricate here. The Fabricate community, it's based on, they are all about Java and containers. And they released an image based on Java, on Linux Alpine, that has some interesting features. The command that runs the jar here, it's a shell script that reads the C group memory information to know that is running inside the container what is the max memory and what is the core limit of that container. So with a small change here, let me show the changes to use Fabricate. So I'm using Java Alpine Fabricate. I just specify the name of the jar, and then I place this jar file inside the deployment folder. I don't need to run any specific thing because everything else will be executed by this run Java shell script. So let's run this application here using Fabricate. If I run the Fabricate image with no memory limit, it will just run a Java with some configurations here, like parallel GC, but nothing specific to memory. But if I change here and say I want to run a container with 50 megs, 150 megs, it will automatically do the calculus to you and create a maximum amount of memory of 130, 1/4 of the limit of the container. It will be applied to the heap space. So if I specify 300 megs, you can see here 75. And if it's more than 1 gig, if it's more than 512 megs, for example, if I specify 1 gig of RAM, now it will change the ratio to half. So it's automatically. I just ask to run, and it will do the calculus automatically for me, for myself. Okay, but if we want to explore a little bit more, we don't need to create this kind of application just to try, especially because, just to share with you something important, most of the time, this calculus is based on that API that I showed to you. Runtime, get runtime, max memory, and runtime, get runtime, available processors. The problem is that most of servers use those APIs, like Tomcat. You can see a lot of usage here, Wildfly, Vertex. But it happened very frequently in Java 8, and it was patched. The problem started when Java 8 was the latest version, but then they released Java 9, and they applied a patch to fix this. With OpenJDK, you can do something like, you can get the application and run java-show settings VM-version. So I'm using here OpenJDK 121 with no special command. When I run that, you will see that the maximum heap size is calculated to almost 2 gigs, which is 1/4 of the 8 gigs of my Docker configuration. Okay? But since they patched Java 8, now in Java 8 update 131, so here I ran update 121. Here I'm running update 131, and it has some things that you can enable in the JVM, like unlock experimental VM options, use C-group memory limit for heap. So it will the JVM itself, it's not a script, the JVM ergonomics itself will run C-group to calculate the limit for heap, and then we can see that in a container with 100 megs, the limit is, the maximum heap size estimated is 44 megs. Okay? But if we take just the latest JDK 8, no update here, just the latest, the one that came from Docker, if we run, it will get also the memory limit from the heap, from the container. So I specified here 1 meg. The limit is almost the half, 48 megs, with the updated to 12, because that's the latest version. So you tend to think, okay, it's fine, it's just to use the latest Docker tag and I will be covered. I will not have any problems just by using the latest JDK, right? But usually people who are maintaining those Docker files, they patch something behind, but they didn't patch for example, they patched Java 8, but they didn't patch Java 9. So if I run Java 9, the latest version, it shows almost 2 gigs. Remember, just changed it here from 8. 8 was patched. You can see here for the 8 megs in a container with 100 megs. But Java 9 was not patched. So it's important for you to know that this problem happens and identify that when it happens to you, it might be a different version or a different or a version that it was not patched. Okay, so for example, if I get that application that's running with Java with the raw JDK 8 with, again, 8 gigs of memory, and I access my endpoint because I specified a container, a container with 600 megs. That's the command that I ran. Then it calculated to 1/4, 150 megs. But if I change the application here to use JDK 9, which was not patched, if I try to run the application, you can see here it will eventually crash. Come on. Crash, crash, crash. Yeah, you can see that's trying to allocate memory. It takes more time. Yeah, and it was killed. So you can, it's important for you to know that, because you can think, oh, but it runs on Java 8, but I updated to Java 9, now it stopped working. Why? So with those commands, you can have a diagnostic on why it failed. Okay, but fortunately, with Java 12, the problem is really solved. By the way, in Java 12, you don't even need to specify use cgroup memory limit for heap, because that was deprecated, so it doesn't recognize, and the application will not run. So if you are using Java 12, you can just remove that specification here, that configuration, and it will automatically say, okay, you are fine. I know that you are running inside a container. I know that this container is limited, and I will configure my ergonomics to just allow half of memory. Okay? Now related to CPU, we learned about the things that can happen with your memory limit. But now let's take a look on the CPU usage. I have here also a special endpoint. I'm running Java 9, and just as you learned here, Java 9 is not patched. So if I access this endpoint here, it will show two processors, although I said here that I'm limiting to 1 CPU. Okay, because Java 9 was not patched. But if I change that to JDK 8, although I have 2 CPUs here, but I limited the container to 1 CPU, if I refresh, I will see 1 processor. Okay? So unless you are using Java 12, but with this pace of a Java release every 6 months, it's hard to keep your production environment always updated to the latest Java version. So if you are not using Java 12, it's good for you to know about these possible issues. To show how you can configure your Docker or your container to handle the CPU usage better, I have here an image, a Java image called distressed, that allows to allocate CPUs. So what I will do now is change my Docker file, my Docker daemon, to have 4 CPUs allocated. And while it's starting, I have a small, I have a space for one question, if you have one. Nope? Fine. So this application here will start consuming how many CPUs I request. So in this case, I have 4 CPUs in the Docker daemon, and I will ask to stress 1 CPU only. So it's starting to stress the CPU. If I run Docker stats on this side, we can see here that's running 100%. 100% means 1 CPU. If I can even stop it here and say I want to stress the 4 CPUs that I have. You will see 400%, which means that 4 CPUs are being consumed. But what I will do now, just one point to let you know. I have 4 CPUs, and I'm requesting to stress 4 CPUs, so it's given me 400%. What happens if I ask to stress 8 CPUs? I don't have 8 CPUs, right? So how many percent do you think that it will show on the stats? How many? 400. Yes, 400, because I just have 4 CPUs. Although, and then I start having a collision contention problem here, because it will have to coordinate the requests on the CPU, although, like if it was 8 CPUs, but I have just 4. But Docker allows me to control the CPU limit as well. So what I will do is limit the CPU usage to just 1. So I'm limiting the CPU usage to 1, but I'm requesting 4 CPUs. In this case, you will see that the same issue. Although I'm requesting 4 CPUs to be stressed, Docker restricted me to see just 1 CPU, and it's creating an internal contention. It will not kill your application if it tries to run more, but it will create a contention because I'm requesting more CPUs. Now, what if I change that to, by the way, this is not a good thing to do because I have 4 CPUs, but I'm just running 1. What I can do here is, first, request 1 CPU, but using the CPU set configuration. The CPU set configuration says that I will run, that I will use in a set of CPUs just 1. So now I can request 4 CPUs, and I will see 100%, right? Let me just change here. 100%, because I'm limited to 1 CPU, although I'm trying to stress 4. And now I will run the same command again, but restricting to another CPU. So this, CPU set 2. CPU set 2. Now I have 2 processes limited that are trying to consume 4 CPUs each, but they are limited to 100% each one of them, because here I'm using the CPU set CPU 2, and here CPU set CPU 1. So 4 CPUs, I have 100% here, 100% here. If I use the same parameter on both will try to compete for the same CPU number 1. So if I change here to CPU number 1, They are competing each other for the same CPU. That's why each one of them has 50%. Okay? So if you liked about this talk, I just want to know that you can try by yourself by going to this GitHub link. Okay. As you saw on the slides, you can also go to the Docker blog that explores all these concepts, and also send me questions by Twitter. Of course, we still have no time, but if you have any questions, we can answer that now. Oh, thank you so much.